Good day, everyone, and once again we're back together. All right, so we are looking at question 9 from that IEB exam. Right, let's get right into it. So they say to us, we've got a metal ring that lies on a table. The south pole of a magnet moves vertically downwards, right, towards the metal ring from above. Right, so they say to us on the diagram above, draw the magnetic field lines around the permanent magnet. Now, what we are going to do, ladies and gents, please remember, when I have this kind of a drawing, I'm going to first make sure that my magnetic field always goes from north to south. Okay, so on any magnet, right, our magnetic field has to go from north to south. Okay, so my north lines have to be in such a way that, right, they're moving out, and my south lines in this case would be moving in towards the magnet. Okay, right, so that would be the kind of drawing. Please make sure that those lines don't cross each other and that they are attached to the magnet as well, right? All right, so the next question, they say state Lenz's law, right? So please remember, okay, so this is where we're going to capitalize. They say to us, or rather, as Lenz's law simply says, the induced current, right, flows in the direction so as to set up a magnetic field to oppose the change in magnetic flux. Okay, so remember the magnetic field, right, has to rather oppose the change in magnetic flux. Now, if I look at this, from above, in fact, let's go on to the next question, right? So they say to us, when viewed from above, right, does the change, or rather, does the current flow clockwise or anti-clockwise in the metal ring? Now, please, guys, I want you to note this. So in a metal ring, remember, we said, according to Lenz's law, we need to make sure that the magnetic field opposes the change in magnetic flux, right? So I want you to note the change in magnetic flux in this case obviously would be going down, right? So now I want to make sure that my magnetic field goes up, right? I want you to think about it. I want my magnetic field to go up. So as a result, now, if you think of Lenz's law, we are going to use our left hand in this case, right? And you'll see that if you curl your left hand, in order for your field to be pointed upwards, you have to curl your fingers, clockwise in order for the field to go up. So in this case, it means that we have to curl clockwise, or rather the direction of our current will be clockwise in order for it to form a magnetic field that is upwards. Okay, right. Now, they say to us, explain, right, why current flows in the metal ring. Right, guys, remember, in this case, we are just simply going, it's almost like stating, Faraday's law in a sense, right? Now, we can simply talk about the change in the magnetic flux there, right? That as the magnet falls, in this case, the strength of the magnetic field right around the coil will increase, or the change in the magnetic field will increase in this case, causing a change in the magnetic flux. Okay, right. So remember that whenever you change magnetic flux, it will always induce a current. Okay, right. And please, we need to remember all of that. I won't write it down, but as I've stated it. Okay, right. Let's go to 9.1.5. They say, suggest one way in which the current induced in the metal ring could be increased, okay, to this magnet, right? So what could we do? We could move the magnet faster, right? Remember that the faster we move the magnet, in this case, the more we can actually cause a change in the magnetic flux, and that the greater the change in the magnetic flux, the greater the induced EMF in that case. Okay, right. All right, now the next part, they say define magnetic flux linkage. Right, and remember, so whenever you look at that, that's going to be change in phi. All right, so that's B times A, right? So all we need to do is to talk about what it is. In this case, it's the product of the turns of a coil and the flux through the coil as well. Okay, right, so the product of the turns of the coil and of course in this case as I had said, and the flux through the coil. Right, so 9.1.7, right, they say explain how the induced current would change if the metal ring was replaced with a coil. And guys, I want you to always remember, once you replace the ring with a coil, what are you now increasing? The number of turns, right? The number of loops that are formed. And in this case, the greater the number of loops, all right, the greater the amount of current that we would form. Okay, right, so that'd be greater flux in this case, and therefore more current would be induced. All right, and then let's go on to the next portion. Right, so they give us that diagram there. They say you have a uniform magnetic field as shown in a loop of wire. Now remember, whenever I see X's, right? So when they give me that X like that, it shows me that the current is going into, the field is going into the page, right? So we know that we will have our fields going into the page. Now they say to us, in relation to your page, what is the direction of the uniform magnetic field? Okay, we've just answered that. That will be into the page. So I want you to note, what would out of the page look like? It would be dots like that. Okay, so we always imagine it as though it's an arrow with some X there. So when you see the X, it means it's moving away. When you see the dot, it means you are looking at the head of that particular arrow, right? So in this case, it means that it's moving into the page, right? And then finally, they say to us, describe two ways in which you could generate a current in the loop, in the wire loop, right? Using a uniform magnetic field shown, right? Okay, so how would we generate current in this case? We can we can try to move the loop into the magnetic field, okay? So we would move the loop, move loop into field, okay? And we are going now to apply Faraday's law. What can we now do to the loop, right? We can rotate it, right? Remember, we can just simply rotate it to cause that change in magnetic flux. And so we can rotate the loop within the magnetic field. The magnetic field, okay? Right, so that is how we would answer that question, all right? Okay, right, it looks like that is how that cookie crumbles. And please, guys, don't allow this section to give you heart palpitations. It's a very small section, all right? Remember, whenever we use, the law or the Faraday's law, we're going to use our right hand. And of course, on Lenz's law, we're going to use our left hand. All right, so I'm going to leave it there for now. Okay, I'll see you guys again next time. Shap, shap.